All right, so a little bit about me. This is actually my first conference ever. So not only am I an attendee, I'm actually speaking for the first time too. So this is pretty exciting for me. It was nice to meet a lot of you guys. Hopefully I'm able to meet even more. So I'm originally from Minnesota. I moved out here to California a few years ago, mainly for work, also for the weather. So I'm a former product security engineer at Intel. I worked on GPUs, compute accelerators, MPUs, all that kind of fun stuff. I'm currently a security engineer at Amazon. In my free time, I really like to focus on firmware and hardware projects. I love embedded devices, and I love debugging. My handle online, if you have not heard of me, is ODG, Oscar de Grach. And my LinkedIn is there if you're interested in connecting and chatting a little bit. So we'll jump in. So the Samsung Galaxy S4, this is a flagship Android smartphone that was released in 2013. So this is Samsung's premier smartphone during that period of time. This device runs on the Qualcomm APQ 8064 system on chip. So there's two different kinds of Qualcomm SKUs for their SoCs. They have APQ, which is just an applications processor, and they also have MSM, which stands for Mobile Station Modem. That includes the SoC inside of it. It has a modem as well, where the APQ is just a standalone processor. So this device has a quad-core Crate CPUs, which are, to the best of my understanding, most likely based on Cortex A9. Give or take. It has 16 gigabytes of eMMC from the supplier Toshiba, 2 gigabytes of RAM. It was released with Android 4.2, so pretty old, very old. And it has a locked bootloader. So we'll jump into it right away. Here's the boot flow. So on the far left, you can see the PBL, primary bootloader, which is our boot ROM or mass ROM. That boots from an ARM7 TDMI core, which is like sort of a basic 32-bit applications core from like the late 90s, right? So it's pretty old, pretty simple core. And that loads and boots into SBL1. SBL1 is the secondary bootloader, is what they call it. That also boots on the ARM7 TDMI core, and that stage of boot actually bootstraps the applications processor. So the next phase in boot, once that is bootstrapped, we go into SBL2, which is when the Cortex or the application processor actually takes over execution. From there, you can see on the bottom path there, we go and we load TrustZone, which is like the secure hypervisor for ARM. And on the top side, that ARM7 TDMI core that we booted from gets a firmware image that runs resource and power management. It's known as the RPM on the system on chip. From there, we go into SBL3, which is another third stage bootloader. I'm not really sure why they need so many bootloaders. And then we go into LK, little kernel, which is the Android bootloader, which is sort of the end of the path until we boot into Linux or the Linux kernel for Android. So looking at these early stage bootloaders, the SBL1, like I said, boots on the ARM7 TDMI core. So this bootstraps the application processor. It also initializes the power management IC. It initializes the storage, so we have eMMC gets brought up. And this is also responsible for JTAG re-enablement via a custom OU within a certificate that they use for OEM internal use only. This is for debugging. So there is a write once register, which we'll cover a little bit more later. So as this certificate is parsed and the image is loaded, it looks for that field, and if that field is set, JTAG is actually re-enabled. Otherwise, it's disabled by Fuse. So we can't re-enable it any other way. When we go to the second stage bootloader, SBL2, Cortex-A, so we're on that applications processor now. The applications processor gets initialized. We bring up our DRAM, so we do DDR configuration, all the training, all of that good stuff. We enable our cache, we enable MMU, and like we discussed earlier, we load TrustZone and we load RPM, the resource and power management. From there, we jump into SBL3, which mainly does security configuration. So from there, we do some fuse provisioning and checking. Depending if the device is brand new, it'll blow a couple different fuses. And it'll also check things like rollback and a couple other fuses. At this stage, there's also basically a hypercall into TrustZone that disables fuse writing, which is called the milestone. So that's what Qualcomm's terminology is this is the milestone. So they set that little flag within TrustZone, so it's in secure memory. You can't, access it otherwise from user space or kernel, right? So once that's set, fuse writing is done. And we also load the Android bootloader at the end of all that. So then LK takes over execution, and from there, we begin loading Android. Okay, we're back. So the Android bootloader, little kernel, right? This is pretty common with Android bootloaders. I'm sure there's a lot of different variations of the same little kernel source. I've seen it used across a ton of different manufacturers and OEMs. So Samsung in particular uses a proprietary USB protocol called Odin. So they don't actually use fastboot. This is a little bit different. We won't go too far into details on that, but essentially when you're flashing an image, it gets compressed into a tarball. And from there, each image is parsed, and then they check the signatures on those images that are appended to the end. That's a Samsung implementation. And they also check the rollback, which is stored in that certificate that we talked about earlier with that debug field. So there's actually an anti-rollback field too that's called software ID. So that field is checked, and if that field is incremented, then we also will blow the anti-rollback fuse to increment it. So during a later stage in boot, there is something known as like a developer edition of these devices, right? So later in the stage of this boot, it actually checks for a developer signature. So it's an RSA signature that's at like a fixed sector towards the end of the eMMC. So we'll take a look a little bit more. So looking at how to actually unlock the bootloader from what we talked about, this is the function that actually checks to see if the device is unlocked. And essentially what it does is we're hashing the eMMC CID, which is a unique register to each card. It's 128 bits, and it's write once at factory. So you should never be able to set this, allegedly. Maybe we'll talk about that sometime in the future. So these developer edition units have an eMMC CID hashed, and then they're signed with this RSA key, and then they're appended at that fixed sector towards the end. So during boot up, we do the hash of the CID, and then we verify the signature and compare the hash within that signature. And if it matches, then there's a flag that's written called the developer flag. And that actually enables unsigned boot code. So we can boot custom boot images, custom recovery images, and that enables us to more or less have an unlocked bootloader. So if we tear down the device, this takes a little bit, but I could probably do it in 3 minutes now. I've done it so many times. The device here, you can see on the back side, we have the SIM card, the micro SD slot, and then we have basically all of our ICs on the side here. And we'll take a look a little bit more at that, but just so you guys can see what the PCB looks like from the inside. So if we do a teardown here and we actually sort of dive in and see what everything is, you can see in the red box there is our system on chip. That's the APQ 8064. We have our modem, the MDM 9615, which is also a Qualcomm modem. We have our Toshiba eMMC down on the left there, and we also have some interesting pads sort of at the top. I'm sure most of you are familiar with taking devices apart, finding debug ports, so obviously that sticks out like a sore thumb, right? So I went through, used a multimeter, trial and error, and discovered every single pin and figured out all the functions. And if you're familiar with JTAG, you'll recognize a lot of these pins here. You can see the bottom two right here. These are for serial. You have a ground, and then the rest are JTAG pins. So what is JTAG? JTAG stands for Joint Text Action Group, and it's part of the IEEE 1149.1 standard, which defines test logic that can be included into an integrated circuit. This is meant to replace more expensive and complicated testing and verification that had been done in the past. So there's things like bed of nails where you literally have, like pogo pins that interface with the actual PCB. You set it down and you have pins for every single pin on the board. Obviously, that's expensive and complicated to do, so there's an easier way to do it if we do it internally. So we have this logic internally that allows us to do quite a few different things that we'll cover. You can see that we have 4 primary signals. It looks pretty similar to SPI if you're familiar with SPI. So we have TMS, which is a test mode select. We have TDI, test data in, TDO, test data out, and TCK, which is test clock. And then we also have a couple optional pins, which is T reset, which is tap reset, which just resets the tap controller, which we'll talk about in a little bit. We have S reset, which stands for system reset. That resets the whole board and all of the ICs. And then we have what's called return clock. That's not a part of the IEEE 1149.1 standard. Usually this is only on like ARM7 and ARM9 cores, which are pretty old. This allows to do like adaptive clocking. So you can actually control the clock based on some logic inside the CPU without having to configure it yourself. So JTAG is often used for debugging and programming as well, and we'll talk a little bit about that. But if you notice here, typically, like on a typical system on chip, you'd have a few different devices, right? For example, you might have a flash controller, you might have a DSP, and you might have a CPU core. So actually, all of these are connected to each other. And so when you shift data through one, it actually goes through all of them. And you use that TMS pin to select sort of what endpoint that you want that data to go to. So one of the, sorry about that. One of the downsides to this is that there's sort of a limitation of how fast you have one, for example, you have one IC that maybe can't handle quite as fast of a clock as this one. You have to use sort of the lowest common denominator, right? So there's sort of a downfall of that approach where if you want to do some sort of like high-speed tracing or testing like that, it makes it difficult when you have these really slow devices on the chain. So we talked a little bit about tap controllers. So a tap controller is the actual logic inside the chip that actually controls the JTAG. And so it stands for test access port, and it's essentially just sort of like an endpoint right on that daisy chain that we looked at earlier. And so it has what's called instruction registers and data registers. The data registers vary in size based on the instruction register. So we have sort of an example here of multiple instruction registers, right? We have a bypass register, we have an ID register, and all kinds of other registers. So in this ID register, when you do a tap reset or reset the device, this instruction is actually automatically selected so that when you read out from this tap controller, the first thing that you see is the ID code, so you can understand what device you're actually connecting to. These are generally unique per platform. Sometimes that's not always the case, but generally, you'll see a specific ID code for a particular platform or particular architecture, something like that. We also have what's called a bypass instruction, and this bypass instruction, basically, you could consider it putting your device into standby. So it skips that device when you're shifting data through. It doesn't connect to the instruction registers, just meant to sort of bypass and ignore that device. And we have what's called boundary scan. So this goes back kind of what I was talking about earlier, where we use this for testing ICs and doing verification. So you can see around the outside, they have these I/O pads, right? And so some devices have this boundary scan chain. And so these are actually all of the pins on the device, the GPIO, your SPI, maybe an SD or eMMC interface. All of that stuff is actually connected to this boundary scan chain. And there's usually anywhere between 2 to 5 bits that represent each pin, and each of those pins would be, the state of the pin, maybe there's muxing of the function, so you could probably change the function, you can change the polarity, things like that, right? So that's what it's, I'll try to make sure this doesn't happen as much. And so one of the interesting things is that a lot of manufacturers will include what's called a BSDL. Generally, For some manufacturers, you need like an NDA to get access to this kind of stuff. Some of them publish it openly. But essentially, it's a list of pins that describe in what order these pins are in that register and what all the bits mean, and also the different instructions in these instruction registers and what they do. There's some common instructions that we'll probably get into a little bit here that we'll talk about. So some of them are kind of generic, but one thing that's kind of interesting about boundary scan is you can actually use it to sniff on different interfaces that are inside of the chip, right? So we can look at a UART interface. We can actually sniff the data off the UART interface. We can also do that with I2C. We can do that with SPI. It's kind of handy from that perspective. The only difficult part is if you don't have that BSDL, it's really hard to know what pin is which. So let's take a look at some of the JTAG debuggers. These are the devices that we would use to actually connect JTAG. So we have kind of two different categories of devices is the way I organized it, but essentially we have commercial debuggers. Usually they have like a high-speed interface, USB 3.0 or LAN or Ethernet, something like that, right? So we can do things like tracing, which is a very, very data intensive. There's a lot of bandwidth that's required because we're constantly monitoring what's going in and out of the registers and that kind of stuff. So generally you'll see devices that support tracing have extra pins on top of JTAG so we can actually get that data aside from the JTAG pins. Usually there can be anywhere from I think 20 total for ARM, and then all the way up for if you use like Intel JTAG, like XTP, I think has like 68 pins or something like that. So quite a few pins. They usually often have low latency memory for tracing because you need to get that data essentially read out and stored really, really, really fast, very fast. And like I said, there's a high volume of data coming out when you're doing a trace. Often the software is proprietary for these commercial debuggers. I'm sure if some of you are familiar, there's Louderbach. They make a product called Trace32. DStream, JTrace Pro, which is sort of, I'd call it like semi-commercial. But the one thing that all of these commercial debuggers and software suites have in common is that they're really expensive. Then we have open source and common debuggers that you've probably heard of if you work with microcontrollers and that kind of stuff. So generally they have like a USB 1.1 or 2.0 interface. Rarely ever actually use all that bandwidth. And you'll usually see like an FTDI serial chip in those types of devices. Those are really common. There's ST-Link, which you can reprogram like an ST microcontroller to act as like a debugger. Same thing with NXP's LPC chips, the LPC Link 2. You can even use a parallel port. People actually used to use parallel ports to unbrick their old Linksys routers, if you guys remember those from back in the day. So these usually have minimal or no tracing support because they don't support all the pins, usually requires some more complicated software, but they're generally pretty cheap. Some of them are more expensive than others, but I mean, you're talking like anywhere from 15 to 30 bucks, so it's not bad. So where do we start if we want to actually access the Samsung Galaxy S4's JTAG pins? So we could look at commercial products like we talked about before, like Louderbach, Trace32, DStream, JTrace Pro. But the commercial options are really, really expensive. They're difficult to acquire because they're generally over $10,000. Sometimes you have to sign NDAs because manufacturers will have certain functionality baked into that program that isn't accessible generally to the public. And often they have really steep learning curves because they have their own environment sort of where they have, all kinds of different commands and stuff to do some particularly complicated debugging. Another option that we have is called OpenOCD. I'm sure many of you have heard of this before. It's an open source on-chip debugging software, and it supports a lot of the cheap debuggers out there. It has somewhat of an esoteric configuration for those who are not familiar with JTAG, and it may not support things like TAP routers, which we'll talk about in a little bit here. There's also gray market solutions for aftermarket repair and programming. You see these sort of in a lot of third-party sort of like cell phone repair shops. They're more common overseas, but often you'll also see them because they support things like eMMC or UFS to dump the image data off those kinds of chips. And obviously, all those solutions are closed. The groups who make those are extremely competitive with each other. There's often a lot of attempts to steal IP from each other to implement features in their own software. And generally, you find these people in pretty shady parts of the internet where they conduct their business. But also, often you'll find sometimes stolen IP that they're utilizing for their product. So let's start out with OpenOCD. So I mentioned OpenOCD is open source, interfaces with a hardware debugger. It has GDB integration, which is really great for debugging. So we can actually connect that to GDB. It supports a lot of different architectures, everything from ARM, I think some old architectures from Intel like Quark, MIPS, all of the stuff that you would expect it to. And with OpenOCD, we can halt the core, which allows us to stop execution. We can inspect registers. We can read and write memory. For some chips, we can access flash programming. So we can read and write the flash off the chip if we want to program a new application on it. It's actually cross-platform as well, so you can run this on Windows, Linux, Mac OS, and it's scriptable using the Tickle language, TCL. This is sort of the gold standard for open source debugging. There's a couple other programs out there. They're not as common, JTAG and stuff like that, but really OpenOCD is where most people spend most of their time and effort maintaining. So the first attempt with OpenOCD, you can see my debugger up there. It's connected to those pads that we looked at earlier. We don't have a target configuration. Like I said, it's a little bit esoteric if you're not familiar with JTAG. So I just wired it up, ran the program, and it did, when you don't provide a configuration, it does auto discovery. And so what it'll do is it'll read out the ID code so you can see what the actual taps are on that daisy chain. So what we see when we run that is we see a Cortex-A core site DAP, which is a debug access port that's specific to ARM core site. You can see the ID code there. And then we have the MSM or mobile station modem, which is Qualcomm, sort of like, they call it an ASIC. I don't really know if it actually is or not. But that's their main tap controller for Qualcomm for their internal devices. So when we're trying to look at this device, I was able to sort of create like a generic configuration for this device once I discovered the Cortex-A cores. There's a command once you connect to the DAP that you can dump what's called a ROM table out of the core site logic, so you can actually see what components are connected, get some base address registers to configure the debug logic. But the issue that I had is that it would reset every few seconds. I was never actually able to halt and inspect the system. So we're never able to actually get access to the core. It kept restarting. I don't know if this was a watchdog. Maybe I configured the system reset wrong. Maybe that was the debug disable logic internally disabling it. I'm not really sure what was going on. But like I mentioned, I created that basic configuration file, so at least we had somewhere to start. That's another close-up picture you can see of how I had it wired up onto the device. So enter those gray market repair boxes. So this is a common one. I'm sure some of you have maybe seen this. This is called Z3X EasyJTAG. It's the Z3X group and EasyJTAG is the box. So this is a gray market repair tool that supports JTAG and eMMC or ISP support, so in-system programming. It uses a smart card authentication to protect access to third-party assets they have, so you can download pinouts and recovery images if you want to repair your device. It has a piece of host software which is obfuscated with VM Protect and uses a USB interface on the other side of this box here. It costed about $250 back in 2015. There's only one authorized partner in the United States down in Miami. They activate the smart card and send the device to you. So obviously we need to tear this down. Right when we buy it, let's break it. So we have on the inside, on the left, you can see there's a Spartan Xilinx 3C and FPGA, which is connected to all the I/O pins. And on the other side, we have an LPC 1768, which is based on like an ARM Cortex M3, one of the small microcontroller ARM cores. So just so you guys can see what's on the inside of these things. I'm assuming it uses the FPGA too for doing things like 8-bit eMMC access, which I doubt would be easy to bit bang. So I think that's kind of the purpose of that FPGA, is to do some of that higher speed, like 8-bit MMC access. So this box supports this phone, right? This Galaxy S4. And I don't understand how they can connect to this device, but I can't. So what I did was just dump the PC memory and search for known strings, and that was actually good enough. I found a canned OpenOCD binary with a small piece of loader code that creates endpoints in memory to write to eMMC. So you would write to like a read-or-write region in a command, resume execution of the processor, it would write and then halt, and then you would continue that process, sort of starting and stopping that breakpoint as you write into those endpoints. The firmware for this box is encrypted. The LPC 1768, which is that ARM Cortex M3 microcontroller, had CRP3 enabled, and if any of you did the glitching class or the training on the STM32, it's similar to RDP. So CRP stands for Code Replay Protection. And when that's enabled, JTAG is disabled in that box, the flash is locked, and IAP access is only enabled, which stands for in-application programming only. So your user application has to do the programming in the flash. So we can't see actually what's on that unless we want to get into glitching that or doing something like that. So I actually found the init script just sitting in memory as well for my device. So I'm not really sure why VM Protect didn't protect this stuff. But I'm not much of an x86 guy, so at least it worked out in my favor. So this is what the configuration file looks like for OpenOCD. Some of this stuff is custom to Z3X, but you know, it's ultimately just kind of pointing out the ID codes on the chain, which are the taps, and then defines the CPUs, what kind of CPUs they are, and the location they are on that chain. And then these guys do some interesting memory writing, right? So they're writing a handful of these different registers, and it's not quite apparent exactly what they are. So we'll take a look a little bit more at that. So after reverse engineering the software, because we had that OpenOCD binary that we discovered, we actually compiled like a similar version and created some IDA Pro signatures. So that, like, the upstream OpenOCD, matched it to the closest build that I could find, and then compared that against what I had in my open source. And there was two different functions that I discovered. One was modified, but it was a standard function. The other was new, that was not present in the upstream OpenOCD code. And also from this prior init script that I showed you before, some of those memory registers that we're writing that we recovered, there's actually a fuse override register that overrides OEM debug configuration. And this resets it to the manufacturer debug configuration. So the OEM can disable JTAG, but they can actually re-enable it with the manufacturer settings, which in this case would be Qualcomm. So there's two sets of fuses for the debug configuration as far as JTAG is concerned. You can see on the right side, this is what the code was when I reverse engineered it. So essentially what's happening is we're shifting in some data into one of the instruction registers, and then shifting in some data into one of the data registers, which would correlate with the instruction register. To note right here, the data that's getting shifted in is LSB first. So actually hex 18 gets shifted in first, and the rest is Fs, and then C0840000. So what actually is happening is the instruction register is getting the MSM TAP is getting hex 18 written to the instruction register, and then C0840000 is the data being read to the data register. So before we go a little bit further, let's take a look at that Qualcomm MSM TAP. So there's a script online that I found in the OpenOCD mailing list that actually will cycle through all of the instruction registers and send data basically through it in order to see how long the register is and what kind of behavior happens. Usually this is meant to sort of reverse engineer like a boundary scan chain, so you can poke and prod at pins and see what changed in between each time you run it, to hopefully identify what pins are doing what. In this case, I sort of went through a lot of these registers and sort of started poking around, and I noticed that the instruction register 17 matched a region in the fuses, which we'll talk about later as well, called feature configuration. And that part of the fuse is actually used to do configuration on the chip. So if you had multiple SKUs, you could disable different IP blocks within that chip. Things like the modem, things like certain codecs, for video and stuff like that. So you can actually reconfigure these devices to enable IP blocks if you're in the know-how. But one thing I noticed is that we were talking about that instruction register at hex 18 here. And so whenever I scan that register to see how long it was or what it was doing, it actually causes issues in the daisy chain. I lost connection to the taps and everything reset, and sometimes it would cause a lot of issues, right? So enter Google's patent search. Taking a look around, I found that Qualcomm has what's called a TAP router. And so with this, what you can do is actually splice taps in and out of the daisy chain. So that way, if you want to do some high-speed operations on a particular chain, you can remove all the slow ones and put the fast ones in. The disabled ones are frozen, sort of, if that makes sense. And then on the bottom right, these are all the different taps that I discovered within that core, sort of playing around with this register. So here's a diagram from the patent. On the left side, you can see sort of the muxer for all the different cores and how they're interconnected, and then there's some enable bits. And at the top, if you notice, this looks just like our tap controller, right? We have our instruction register, we have some data registers, and that daisy chain JTAG configuration register is connected to a decoder, which is connected to those enable bits that's connected to those different taps. So that's how we're splicing in and out those taps on the chain when we want to choose particular core to debug. So we looked at this a little bit earlier. This is the actual code that is doing the configuration of the daisy chain here on that daisy chain controller configuration instruction. So this is the next piece of code that I reverse engineered here. We have an instruction common to ARM called scan N, and this actually selects like an internal scan chain on the ARM core. It actually has its own scan chains internally as well. So what happens is we select that scan chain 1, which we'll look at, and then we also set the instruction register to 1. And you can see here it has 2 fields that it shifts in. One is 1 bit, and the other is 32 bits. And then we reset the tap controller. So we'll take a look at what comes next. So the scan N instruction allows us to choose different scan chains. So kind of a lot of information here, but the point is you'll kind of see in this next slide here. So we have scan chain 0, scan chain 1, scan chain 2. You can see on this ARM7 TDMI core, we have access to some of the CPU logic in scan chain 1. We have access to embedded ICE logic, which is sort of like the debug logic for ARM-specific stuff. And then scan chain 0, which sort of connects all these cells together. These are the different scan chains that we talked about. So 0, macro cell scan test, debug, and then the embedded ICE logic programming. So that's where you can control like watch points, breakpoints, and other types of debug configuration. So scan chain 1 is particularly interesting because that's the one that we just configured here. And so when we look at what actually is happening, in the ARM specification, you can see that there's a data bus and there's also a breakpoint signal in the 33rd bit. And if you just focus kind of on number 1 and number 2 here, it enables a known value to be scanned in when we're in test mode, which is one of those instruction registers that we can use. And another instruction register is called X-test. That's generally the different types of modes that you can operate on, like a boundary scan chain. And so when we enter X-test mode, we can actually scan that value and capture it into this chain here. So if we take a look about this breakpoint signal here that I talked about, it's a conditional request for the processor to enter the debug state. So when we enter the debug state, we can actually halt the core. That's how the core is getting halted. And if you notice at the very end here, this enables extension of the internal breakpoints provided by the embedded ICE RT logic, which is where we have our breakpoint controller and things like that. So this is the next part of the data or the function that I reverse engineered. And you can see we actually enter X-test mode. So we're capturing that bit that we just shifted in right here. So you can see there's a 1 set in that breakpoint. So we're setting that 1 in that register, and then we're enabling that to be captured by the chain here. And so what happens, you notice the size of the scan here, 5.1, 32.5.1. So I noticed something that was kind of interesting when I was going through the ARM manual. If you notice this here, 32.5.1, and this is access into the embedded ICE logic on the chip. And then here you have these watch point registers which control breakpoint and watch points. And then you have an address decoder at the top in that 5-bit field there. And so there's all these different registers in the embedded ICE logic here. We have debug control, debug status, and then we can configure watch points, which either watch point or breakpoint, depending on a certain condition, that would actually halt the core. So here's how we actually disabled it and how I found out how they were doing it. So what you do is you actually connect to the ARM7 TDMI core using that JDCCI instruction that we talked about earlier. You select scan chain 1. You set the ARM7 TDMI instruction register to 1. You shift those 33 bits of data in. The 32 bits are data bus, and then you shift the breakpoint so the bit is high, so we set it to 1. You reset the tap controller, and then we'll set the instruction to xtest, which captures that input that we just shifted in. You can see right here, and then we do those 2 embedded ICE register reads. One of them lacks an address in the scan data. I'm not sure why, but it seems to read out the embedded ICE register anyways. I'm not quite sure why, but at that point we reset the chip quickly. And if it's done correctly, we'll actually, OpenOCD will try to, on its own, without any of this modification, set a catch-all breakpoint in that embedded ICE logic, which we just enabled using that prior command. And so when we actually catch that, we can write to memory. So when we catch that breakpoint, the device is halted, we can write to that override register. The timing is sort of delicate on this. You have to do it really, really, really fast. Otherwise, it can be difficult. So here's the device. We've got it halted now. We've got access to the applications core, and we're in SBL2. That's the address in the program counter there. So we booted with that ARM7 TDMI core, and we used that same Qualcomm daisy chain configuration instruction to switch back over to the Cortex application core. We now have secure access to JTAG. We can debug the bootloaders, we can debug TrustZone, and we have full access to everything. This is just a screenshot of IDA Pro as we're single-stepping through the boot ROM, which you're not supposed to be able to do. So you can see here, this is where we set a breakpoint and actually catch when TrustZone is being loaded, the secure hypervisor, before we jump into it. So we can actually single-step through TrustZone kernel 2 as it gets loaded. So there's something interesting happening. I kept hitting a breakpoint, and this was a secure monitor instruction. If you're not familiar, it's called secure monitor call, SMC. These are the type of instructions that are issued that communicate between normal world and secure world to the TrustZone hypervisor. And so what was happening is I actually noticed that there was a fuse address in register 2. So it was doing some sort of operation on the fuse, assume read or write. So I reverse engineered the 3rd stage bootloader, discovered that they were accessing the rollback fuses. They were incrementing them every time it read them, even if the version didn't update. So it sort of always wrote. So we'll cover TrustZone really quick. In this case, this is a proprietary implementation by Qualcomm. This is sort of before ARM trusted firmware and Opti, so it was kind of the Wild West. It's a hardware-enforced isolation of secure versus non-secure. Often you see things like DRM, crypto, fuse access, biometrics, and secure storage done in this secure environment. Like we talked about, it communicates with normal world via SMC instructions. It's sort of like a syscall, so it actually goes to a table of services that have various commands that you can access. And then it configures what's called, this is Qualcomm proprietary, but what's called XPUs, which is a system fabric access control, as well as some MPUs. So the fuses, there's a couple different regions here. It's called QFPROM. This is a one-time programmable memory, or eFuse if you're familiar. There's 4 different regions. We have the raw region, the IP block configuration region, which has like a blow timer and other things. There's a corrected region that has FEC enabled, which is forward error correction. So particularly important fuses like the root key hash, maybe an encryption key or other things that are blown in there, and you want to make sure that there's no errors as you pull that out of fuses during the fuse sensing operation. You would use that to make sure that the data is correct. So the raw fuse and corrected fuses are pretty similar. And then in the last bit here, you have a system security configuration and status registers for things like secure boot that show what the status is, and a couple other things like that, like boot configuration, what partition to boot from. And then you have an anti-rollback region that's within the raw fuses and corrected fuses. The corrected fuses is sort of like a shadow region. And so there's also 2 additional spare regions that are used by Samsung for rollback protection. And there's also a read and write permissions region for the fuses itself. So each bit in that region corresponds to a different region in QFPROM. Coincidentally, a lot of the permissions in that region are left open, including the anti-rollback region and the permissions region itself. So we talked about that secure monitor halt earlier, and we actually see through reverse engineering that there is actually a function being called into secure world into TrustZone. So they're actually reading the fuse here. So you can sort of see what's happening here. We have our service and ID, response pointer, the address, the type of fuse, and then the pointers to the buffers of where the data would be either read out or read in to be written to the fuse or read from the fuse. And then there's like a status bit as well at the end that's read out of the register, so you can see how it's going. I'm going to skip forward a little bit. So results, we've got full secure JTAG. We've disabled anti-rollback permanently. We can actually disable the warranty and tamper fuse permanently. We can read the device hardware keys from fuses because System Fabric Security is not yet initialized and was left enabled, and we can access secure memory and so like TrustZone and trusted applications. So I'll sort of skip through this because we're running a little bit tight on time. I found another vulnerability that was just sitting out in the open on GitHub because it was part of the Windows Phone toolkit. Essentially, what they do is they modify one of the partitions, put some shellcode in it, overwrite some secure boot error handler that's in SRAM. That's where you load your shellcode. The shellcode does whatever it does, like you can disable authentication, and that jumps to SBL2. So here's a quick look at the shellcode. So I actually made an addition to the shellcode where you actually can enable JTAG doing that same register writing without actually having to do the JTAG exploit. And then you can see at the bottom that program counter points to right when the register override is written. So that's where the chip was halted. Just a quick dump of the shellcode. And then we have persistence. So we can skip authentication for SBL1, SBL2, or SBL3, TrustZone, RPM, and the little kernel. And this is really useful because we can use unmodified OpenOCD without having to modify some of those functions that cause issues with other cores if we're trying to debug. So just to quickly go through, I know I'm really, really short on time. So I reverse engineered, as any board security engineer would do, the entire bootloader and rewrote it from scratch. I wrote support for the battery, I2C peripherals, display, and all the Samsung specific things, implemented fastboot, a frame buffer console. My wife doesn't allow me to use IDA Pro anymore because of how much time I spent on this. And if there's actually an upstream kernel effort for this system on chip. Someone is actually working on this, and I reached out to see if I could help. You can see I actually dumped out the root key hash and the encryption key, and you can see the JTAG status that I added. So I'll skip the demo. If anyone is interested, definitely come up and ask, but I wrote with JTAG supporting my debugging effort, actually like a full chip emulator. So I can boot through the boot ROM all the way up to hopefully the kernel soon. I just have a little bit more work to do on the crypto engine. You can also extend this into a fuzzer. So kind of an odd disclosure timeline. Found it in 2015, went end of life in 2019, and then in 2024 through a friend who got me connected to this conference. I reported this to Qualcomm so I could present on this. Qualcomm could not get a root cause analysis because someone walked out with the RTL, which is basically the source code to the hardware. So I don't really know why. I never reported it because I didn't know how this worked at the time until I revisited this later on to actually fully understand what was going on. Couple questions. These are some of the ones that I had. So to save time, I'll just kind of skip to your guys' questions here.
All right, thank you for your talk. We can do a few very quick questions.
It was in one of the slides that you skipped, but can you just speak to what was the disabling of the anti-rollback mechanism?
Yeah, so that was that fuse permission region, right? So you control the access, it's like an access control to the fuses. So what we did was we disabled the read permissions on the anti-rollback region by writing to that fuse permissions region, which the fuse permissions region has its own access control that was left wide open for reasons I don't really know, but it was pretty convenient for this purpose.
All right, one last question because we're a bit over time.
Why spend years on a 13-year-old SoC?
It was a great learning experience.
All right, thank you very much. Let's thank the speaker again with applause.